Okay, so we are going to talk about in chapter 4 probability. And with probability, you may have seen, for example, flipping a coin or drawing a particular card or any number of things. But probability can be applied to business in several different ways, and we're going to look at that by looking at an introduction to probability rules for more than one event, and the counting principle. So, probability is a numerical value ranging from 0 to 1, and it indicates the chance or likelihood of a specific event occurring. If there is no chance of an event occurring, we give the probability a value of 0. If the event is going to absolutely occur, we give it a value of 1. So, the process of measuring and observing an activity for the purpose of collecting data, we'll look at, for example, rolling a six-sided dice, or looking at a sample space where all the possible outcomes or results of an experiment. The sample space, for example, with the dice is 1, 2, 3, 4, 5, 6. We know the possible outcome. We know the possible outcome of flipping a coin. It can only be heads or tails. So sometimes you know what the chance is. For example, a dice is 1 in 6. Flipping a coin, heads or tails, is 1 in 2. But you don't always know that. So we're going to look at these different events. So in an event, this is one or more outcomes of an experiment. For example, if I flip the coin, it's going to be heads or tails. The outcome or outcomes is a subset of my sample space. An example of an event are rolling a pair of dice. If you had a second dice, that's going to change the outcome of the event, because then you'll be rolling 2. So you're not having just 1 in 6 chances, you're having 1 in 12. A simple event is an event with a single outcome in its most basic form, and it cannot be simplified. An example of a simple event is rolling a 5 with a single dice. So here are some examples of some sample space examples. You've got flipping a coin, answering a multiple choice question, is answering a true-false question. Is it true or false? Inspecting a product. Sometimes we get products that are defective, and in business we're going to be looking at what's the likelihood that the product is going to be defective. And sometimes you have recalls on products because so many have ended up being defective through statistical measure. Drawing a card from a standard deck of cards. You've got 52 cards in a deck. What is the likelihood that you're going to draw an ace? We're going to look at that. So, methods of assigning probability. There are 3 distinct methods. There's classical, there is empirical, and there is subjective. So, with these 3, let's talk about these 3 types. You've got, with classical, this is used when you know the number of possible outcomes of the event of interest. For example, looking at, and I was having some trouble with my pen. Let's see. Okay, now it's working. If we were to look at classical, for example, you've got the number of possible outcomes that constitute event A over the total possible outcomes of a sample space. For example, if I'm going to look at flipping a coin, it's a 1 in 2 chance of flipping heads or tails, because there's only 2 possibilities of that event. So looking at the dice, there are 6 possible ways that you can roll the dice. 1, 2, 3, 4, 5, 6. And the event of rolling a 5 would be a 1 in 5 chance excuse me, a 1 in 6 chance, because there's 6 possible, there's 6 sides on a dice. So the chance of rolling a 5 would be a 1 in 6 chance. So here you see 1 in 6. If we convert that to decimal form, it would be 1.67, 0.167%. Looking at it in a percent form, 16.7 percent probability. This is an example of simple probability. So it represents the likelihood of a single or simple event occurring by itself. So let's look at a few other examples. So here you have a sample space where you have 6 possible outcomes of flipping the dice. So classical probability assumes that each event in a sample space has the same likelihood of occurring. This set of events is collectively exhaustive if the sample space includes every possible simple event that can occur. So if you have, for example, and there are some, certain people roll a certain way, you might be more prone to rolling 6s or rolling 2s, on how you hold your hand. In craps, if you've ever watched people play craps, people get to roll the dice, but then they have to change who rolls the dice. So you get to roll until you crap out, so to speak. Then another person gets to roll, and then another person, because everybody's going to roll it a little bit differently. And so you're statistically changing your measure of the outcome or event by changing the people that are rolling the dice. So with empirical probability, the second type we're going to look at, you involve conducting an experiment to observe the frequency in which an event occurs. For example, if you're looking at, say, a toddler and you're giving them 3 colors of balls, they've got red, blue, or green. You're looking and observing how many times the different toddler might pick the red ball as opposed to the blue ball or the green ball. So here you're observing the frequency in which the event occurs. Sometimes, for example, businesses will have trackers or counters where they count and observe how much traffic they may have during a business at certain times of the day. Realtors during open houses track how many times people come and look at the home during open houses. So you look at frequency in which the event occurs over the total number of observations. So if we have 400 new graduates that are asked how much they owe on student loans, here you have a table and you have 400 total graduates in the observation. And I want to know what the probability is of a randomly selected graduate that has between $5,000 and $9,999 in student loan debt. Well, if you look at this, of those observed, I have 102 students that fall in this category. So what is the probability a randomly selected graduate has 20,000 or more in student debt? So with 20,000 or more, I'm going to look at, it's going to change it up, because now I'm not only looking at one subset, I'm looking at 2. So I would add the 66 and 47 together. So here, if I look at this, if I add 66 plus 47 together, I get 102 people. Actually, hang on a minute. Let me look at that. Let's see. Let me back up a minute. What's the probability a randomly selected graduate has between 5,000 and 999. I jumped ahead a little bit, so let me back up. I got ahead of myself, which I sometimes do. So if I look at what is the probability that a randomly selected graduate has between 5,000 and 999, that is 102 over 400. So down here, you've got 102 over 400, which equates to 0.255. Now, if we look at what is the probability a randomly selected graduate has 20,000 or more in student loan debt, and that's what I was looking at, you would have two areas of interest, and you would add those together. So 66 plus 47 over 400. So if you add those together, you get 113 over 400. And if you divide that together, you get 0.2825. So looking at the law of large numbers, this states that when an experiment is conducted over a large number of times, the process is going to converge into classical probabilities. What does this mean? Well, it means that if I'm flipping a coin and I'm trying to count how many heads versus how many tails I have, so if I flip a coin 10 times and I measure or observe how many times it's heads and how many times it's tails, well, it may be that I get 7 heads and 3 tails, even though I have a 1 out of 2 possibility. You might think, well, it's 50% heads, 50% tails, but if I flip it 10 times and I count how many heads versus how many tails I have, I may get 7 heads and only 3 tails. But what the law of large numbers states is that the more you conduct the experiment, the more likely it's going to converge to classical probability. So if I flip it 100 times, I may get more like a 50% outcome of 50 tails, 50 heads. So it's going to be much closer to 50% if you do 100 coin flips or 500 coin flips. So the third type is subjective probability. And with subjective probability, this is used when classical and empirical probabilities are not available. For example, what is the likelihood that home prices will come down next year? Or what's the probability that commercial real estate may crash next year? So, or the probability of inflation coming down, or gas prices going up. This can be, and you're not using experience or intuition. No, you're using experience and intuition to estimate the probabilities of what the likelihood is that gas prices will go up or gas prices will come down. And this could be, for example, a prediction on, for example, if there's a natural disaster like on the coast or an oil spill. Typically, if there's an oil spill, then oil prices go up, making gas prices go up. Or if we have a hurricane hit the Gulf, where a large part of our oil refineries are, that can impact gas prices. So those, based on experience or intuition, that can cause you to estimate probabilities and make assumptions. So basic properties of a probability. For probability rule 1, if the event or probability of event A equals 1, then with certainty event A must occur. Probability number 2, if the probability of event A is 0, then with certainty event A will not occur. Probability number 3, the probability of any event must range 0 to 1. 0 meaning it's not going to happen, 1 meaning it is going to happen. Probability rule 4, the sum of all probabilities for simple events in a sample space must be equal to 1. So, in probability 5, the complement to event A is defined as all of the outcomes in the sample space that are not part of event A. So the complement is denoted as A apostrophe. So the formula for the complement rule is the probability of event A plus the complement is equal to 1. So here would be, for example, my complement rule. This is the likelihood of it occurring, and it's not part of event A. So what that means is, for example, in many situations are going to involve multiple events that could intersect with one another. And a contingency table can be used to show these number of events that are classified according to 2 categorical variables. It gives the example of a deck of cards. There's 52 cards in a deck. And so event A is the card is an ace. Does anybody know how many aces we have in a deck? We have 4. So the complement rule of event A is the card is not an ace because there's only 4 out of 52 that are an ace. Okay? And then event B card is a red card. And then the complement rule card is a black card. So here are your black cards, here's your red cards, here's your aces, okay? Now, you can use a contingency table to calculate simple probabilities. So 4 out of 52 cards are going to be an ace. So the probability of that is 0.077. What is the probability that I'm going to have a red card? Well, there are 26 red cards in a deck, so the alternative is black. So basically, I have a 50% chance that my card will be black. Well, let's look at the intersection of events where the possibility of having a red ace or a black ace could happen. So the intersection of the events, the probability of the intersection of 2 events is known as a joint probability. So here I have a red ace over the total number. So I have 2 red aces and 2 black aces because there's a total of 4 aces. So that's going to be a 2 in over 52 chance, which equates to 0.038 probability. So this is another way you can look at it. The probability of ace and red is denoted as P, and then you've got ace over red and red. So the union of the events of A and B represent the number of instances where either event A or event B will both occur together. So what does that mean? Well, consider the union of ace or red card. So you've got 28 of these cards that are either aces or red, not aces and red, but aces or red. So when we look at this, we've got the possibility of having 28 cards that could be aces or red. So here you've got ace being 2 and 24, and then you've got 2 black aces. So if you add the 26 red cards and the 2 black aces together, you get 28 over 52. So or changes things and the number does go up. Now if you're doing or, you're going to denote it by this as opposed to and, like that. So the addition rule for probabilities is used to calculate the probability of the union of events. So the probability that event A or event B or both events will occur. Two events are considered to be mutually exclusive if they cannot occur at the same time during the experiment. So this is representative of mutually exclusive. Now let's look at this. Excuse me. For mutually exclusive events, the addition rule states that the probability of two events occurring is simply the sum of their individual probabilities. So you've got probability of event A or B, and you've got probability of A plus probability of B. If the events A and B are not mutually exclusive, you've got probability of A or B, and you would denote it by probability of A plus probability of B minus probability of A and B. So here you've got 4 aces, so 4 over 52 plus 26 red over 52 minus 2 over 52 equals 28 over 52 for an outcome of 0.538. So you don't want to count, make sure you do not count the 2 red aces twice. So here you have the probability of event A occurring, plus the probability of event B occurring, minus the probability of A and B. So don't count the common elements twice. That's very important. So with conditional probability, you've got conditional probability. It's probability of event A occurring given the condition that event B has occurred. So here we're looking at event A having a score in the 601 through 800 range. We're looking at math SAT scores with or without a prep class. So I'm looking to know how many fall in that 600 to 800 range with the prep class. So if I look at that, I had 22 fall that took my prep class that fell in that 600 to 800 range. So 22 over 70, because I had 70 total that had taken the prep class that took the SAT, and that would fall as 0.314. If I looked at, let's see. Then if I looked at how many total had taken, how many total that took the SAT that fell in the 600 to 800 range, I had 42 out of 250 students that scored in the 601 to 800 range on the SAT. So I would take 42 over 250 and get an outcome of 0.168 that fell in that 600 to 800 range. So the formula for calculating conditional probability, let's look at this. So, for example, I'm looking at math SAT scores with and without a prep class. So here I've got my prep class, here no prep class, and so forth. So with this particular example, I had 22 students that had taken the prep class that scored 601 to 800. So in event A, you take 22 over 250 total. Because I'm looking at math SAT scores with and without prep. So this changes things. You've got, because here was the total number of students that took the SAT, math SAT. So 22 took the prep class, fell in the 601 to 800 range out of 250. So if they took the prep class and hit the 601 to 800, it's 0.088. Now, B, event B is how many took the prep class. So that would be 70 over 250 that completed the prep class, and that would be 0.280%. So what is the outcome of the probability of A and B occurring over the probability of B? Because I'm looking at calculating conditional probability. I'm known as, so I'm going to divide by the probability of A. So I've got 0.088 over 0.280, which is the same value as before. We're just looking at different ways to look at your independent and dependent event. So looking at the independent and dependent events, two events are considered independent of one another if the occurrence of one event has no impact on the other. If the occurrence of one event affects the occurrence of another event, then they're considered dependent. So let's look at how to determine if events A and B are independent. So we have probability of A divided by B is equal to the probability of A. The probability of A divided by B is not equal to the probability of event A. If this occurs, then they're not independent. So let's look at, with event A, if the grade of 80% or better, event B, interested in the subject. So here you have, we're looking at interested or not interested in the subject matter. 80% or better, rank it this way. Less than 80%, rank it this way. So if you look at how many are interested in the event, in the subject, you've got 72 over 114 that were surveyed. So you've got 0.632 that are interested in the subject. Then if you're looking at how many total scored 80% or better, you had 110 who fell in that category over the total of 200. So 110 divided by 200. And the grade in the course and the interest in the subject are dependent, because if you're more interested in a subject matter, generally you're going to put forth more effort, right? So in this scenario, 110 people or students over 200 total students were scored 800 or better. 80% or better, I'm sorry. With the multiplication rule, this is used to determine the probability of the intersection of joint probability between two events occurring. This is going to be your rule for the multiplication for dependent events. So you've got probability of A and B over the probability of B, the probability of A and B over the probability of A. So let's look at this. So event A, the rain is forecasted. We might carry an umbrella as event B. So P over rain forecasted, you have a 30% chance of rain occurring. If this with this scenario, you're going to carry the umbrella if the rain is forecasted. So you have the probability of A and B occurring equals the probability of A times the probability of B divided by A. So, for example, you've got 30% because based on this rain forecast multiplied by 90% or 0.90 if the rain is forecasted. You're going to carry the umbrella. So 0.30 times 0.90 is 0.27. So there's a 0.27 or 27% probability that it will rain and you will carry the umbrella. Let's look at another one. So formula for the multiplication rule for two independent events. So you've got probability of A and B occurring, and you're going to multiply probability of A times the probability of B. Since these events are independent, you will look at them this way. So what we're going to do is, for example, the contingency table. If you divide 72 over 114 and 42 over 114, you get these percentages. Here you're dividing it by the total and so forth. So with the contingency table, you've got probability of A and B occurring divided by B is 0.632. Probability of A occurring when they're not interested is 0.19 divided by 0.43. Probability of, let's see, A and B over probability of B. So you've got here 0.21 over 0.57. And then here probability of A when they're not interested divided by 0.43. So if they are interested in the subject, you have a much higher percentage of a better grade versus if they're not interested. So just different ways to look at this. I'm not going to give you decision trees. I'm not going to give you Bayes' theorem. Doesn't mean that you can't look at it, but I'm not going to, we're not going to go over this. You won't be tested on it. But let's look at the counting principles. The counting principles I like to compare to a menu or order choices at a restaurant. So, for example, if you're looking at Wendy's and they give you the biggie bag where you can get an appetizer, a dessert, and an entree, how you figure out the different outcomes of the biggie bag and how many different outcomes there are is you would multiply each of those together. So if there are K1 choices of the first event times K2 choices of the second event, you're going to just continually multiply the different possible outcomes together to get the choices. For example, a password combination is another example. So suppose a 3-digit model number is used to be selected using an initial letter A, B, C, or D, followed by two numbers 0 to 9. How many different model numbers are possible? So there are 4-letter choices, 10 number choices for the first number, and 10 number choices for the second number, and so forth. So if there's 4-letter choices, you would have 4 times 10 times 10. And if you multiply that together, you get 400. So you just simply multiply them. With permutations, let's look at permutations. These are the number of different ways in which an object can be arranged in order. So the number of permutations is going to be of n distinct objects. So you have the total number of objects over n minus x. Let's look at this. So suppose you have two numbers are to be selected from A, B, C, D and arranged in order. How many permutations are possible? The number of permutations, your n is 4 and your x is 2. Okay? Now, you're going to take 4 over 4 minus 2. And when you do this, you're looking at the different possible combinations, A, B, A, C, A, D, B, A, B, C, B, D, so forth. So you would take 4 times 3 times 2 times 1 over 2 times 1 because the formula is n minus 1. So when you look at this, you've got 4 times 3 times 2 times 1, and you get 12, 24, you get 24 over 2. And so 24 over 2 is 12. Combinations are the number of different ways in which objects can be arranged without regard to order. So permutations arranged in order, combinations, order does not matter. So if you look at this with combinations, suppose two letters are selected from A, B, C, D. How many combinations are possible? So here you've got 4 times 3 times 2 times 1, just like above. And then you've got n minus 1 times, or n minus x times x. So you've got 4 minus 2 times 2. And so if you look at this, you've got 1224 over 2 times 2, which is 4, which equates to 6. So here the combinations would look like this. So the biggest takeaway here is with permutations, this is order matters, and then combinations without regard to order.